Good day once again. Welcome to Enhanced Impact International Academy, and today we are going to be diving into nature of matter, which is the first topic in chemistry 002. Many people consider this topic a walk away topic or a walk over topic. Trust me, it's a topic that you really need to put your mind into. So before we dive right in, don't forget to subscribe to our channel if you're just joining us for the first time, and also click on the notification bell below so that you can get notified whenever we drop content like this. Let's dive right in, universe. So right now, we have this course outline presented by the E-level board JUPEB, and they want us to talk about nature of matter in respect to phase and phase diagrams, interconversions between the three states of matter. So three states of matter is the keyword there. We're going to be leveraging on just three states of matter. And interpretation of phase diagrams for one component system. Alright, good. So let's start this way. We know we're treating matter right now. We know that we're treating matter. And I feel we should first of all know what matter is. So matter is simply what? Anything that has mass, and occupies space. So literally everything in the universe is matter, because everything is occupying space. Once you are a physical entity, you are matter and you occupy space. Even air itself is matter. Do you get that now? Air itself is matter. One of the proof that shows that air occupies space is that when you take an inverted bowl and try to immerse it into water, you find this pressure that tries to prevent you from pushing that bowl inward. That's because of the air, you understand, inside the bowl that you're trying to also put into the water system. So it's showing you the presence of matter. So air is matter and everything is matter. That's the key thing I want to keep up there. So matter itself are in different phases. For now, I don't want to use the word phase. I'll use the word states, and I will give you my reason later. So matter are in three major states. I use the word major because that's what we're going to be looking at today. And what are they? We have solid, we have liquid, we have gas. Yes. So for other states, we have plasma. We have plasma. We have Bose-Einstein condensate as well. But we're not going to be going into that. So we'll be looking at using these four, because that's what your syllabus will use. In OBJ, in case you ask me about the other ones, just remember Bose-Einstein condensate. One other one that might reflect here, which is not a state of matter. It is not a uniform single state of matter. It's as a result of coalition of two states in respect to the particular pressure and temperature they are subjected to. You understand? And that's your superficial critical fluids. But nevertheless, these are the major ones. Alright, good. So this thing now that we call the state of matter, which can also be referred to as the phases of matter, has a definition you must know. So when they ask you to define phase, are you there now? Phase simply implies a substance that is uniform. That's the key word. Is uniform throughout in two things. Is uniform throughout in both its physical and chemical composition. What am I trying to say? So what I'm trying to say there is, when you look at the physical for a substance that is in phase, that is in a given phase, when you look at that substance, the chemical composition of that substance will be uniform all through. The physical composition will also be uniform all through. Let's take for instance water. So we are talking about liquid water. Liquid water is H2O all through. So all the molecules are H2O. Very good. That's uniformity in chemical composition. Then in physical composition, they all have the same density at different points. You get what I'm saying now? They are all having the same physical properties, the density, the color, all those things there are what make you see that something is in phase. So the phase, in case they tell you to define phase, it's different from defining phase transition. A phase is matter or a substance that shows what? That shows a uniform composition throughout in its what? Physical and chemical properties. In both physical and chemical properties. Very, very good. Now, when I talk about phase transition simply means what? A change in the state of matter. When we say change in the state of matter, this is accompanied by changes associated with Gibbs free energy. We'll get there very soon. Just keep that one side, because thermodynamics is what enables the explanation of phase change. So your phase change is dependent on thermodynamics, which we'll explain very soon. Now, before we start explaining, I want to know what are the characteristics of these three states of matter, because we're going to be employing that very soon. So basically, these are things you know already, that your solids are non-compressible. They are non-compressible. You can't compress solids, right? I can't be solid now and start pressing it together. No, it's not possible. You can't bring the molecules together or try to compress them. That's not possible. Another thing again about solids there is that they have what? They have a definite shape. You understand now? So it's not as if they are assuming the shape of container or a vessel or anything. So that's one thing about them. So another thing again about these guys is that they have a low kinetic energy. So their kinetic energy is low, and that's why their molecules are not freely moving around. So very, very important. One other thing again they have is that they have a high intermolecular force of attraction. They have a high intermolecular force of attraction, so their bonding is very, very strong, and that's what brings their molecules together. And that's what we mean in these solid aspects here. So good. How about when we're looking at liquids? Liquids are a bit more freer, their molecules are more freer, and that's because of the fact that they have a lower intermolecular force of attraction. That's one thing. Another thing again about these guys here is that what? They have a definite volume. When you put a certain amount of liquid in a container, you can easily measure, and that's the volume. No matter where you transfer it to, it's still the volume. So good. So we also have the fact that these guys here, their kinetic energy of the liquid is greater than the kinetic energy of your solids. We are going to employ this in Gibbs energy, explaining to you need to know these characteristics we're writing down here. Alright, so when we go for gases now, it's very important for you to know that these guys, they have no intermolecular force of attraction, and that's why they have the highest kinetic energy, which you see as a result of their movements and all those stuff. These guys are compressible. They are compressible. One thing about liquid again that you can take note of is that liquid, they usually assume the shape of their container. Assume shape of container. You know, when you pour liquid into a container, it takes the shape of the container. Very, very important. Why this one here? This guy here, it assumes the volume of its containing vessel. Very important. Of its containing vessel. Usually this is in ideal cases. So very, very, very good. So these are like the general characteristics of your three major states of matter. I will add one to each of them now, which is entropy. Now remember that entropy, now I told you that Gibbs energy is going to be our criterion. Let me just write it here. Gibbs energy is going to be our criterion to understanding phase transition. So good. Because of this thing that is here, I want us to get how entropy varies in each of the states of matter. So we should know that entropy is simply the what? Entropy is simply the what? Is simply the degree of disorderliness. I'll explain something from that now. It's the degree of disorderliness. So in solid, you see that solids are more compact, right? They are more compact. Their molecules, we said it there, they have high intermolecular force of attraction, so they are more to themselves and they are more organized. That's the meaning. So in this case here, we see that they have the highest entropy. They have high entropy. Why gases have low? These guys have low entropy. Why these guys here, they have the highest entropy? Because they are very disorganized. You know, they have high kinetic energies. When you have high kinetic energy, it means that you have the ability to randomize. You are going to be moving randomly to initiate different kind of motion, like your Brownian motion. So it means that these guys here will be having high entropy, low entropy, because they are very organized. They are less disorganized. Very important. Then liquids here are like we will say they are intermediate entropy. Okay, we'll go with that. Now, You know that there are some systems where you're trying to melt a substance, and while trying to melt the substance, you tend to observe that it was not finished melting. You've seen part of solids and part of liquid. For example, you see ice inside liquid water. That is ice phase of water inside liquid phase of water. So that kind of a thing, it happens. Now the question there is that there are some times when you leave it, it's either the ice inside melts to become complete water, or one way or the other, you find out that the water that was inside now has frozen to join the ice state. Good. That is also a possible condition that can happen during phase transition. So phase transition they are talking about here is not spontaneous phase transition only. It's not, we know that, oh, if you leave it in a spontaneous system, or the ice is going to just melt and become liquid also. Yes, in spontaneous phase. But that's not what we're looking at. They didn't write spontaneous, they just wrote interconversion. So there are different things that will guide those different kind of conversions. What has to happen for what do they call it? For the solid ice to turn to liquid. What has to happen for the liquid to turn to solid? Those are things we're going to be studying in this concept. Okay, good. Having known the three states of matter and their characteristics, the next thing that we want to look at there, we'll define phases, right? I'll define phase. We're going to look at phase diagrams. Yes, we're going to look at phase diagrams, and when we look at phase diagram, we're going to come into interconversion. But just before then, in our interconversions, we know that I'm going to write solid here. Now, right here, I'm going to write liquid here. Write liquid here, I'm going to write gas here. I write gas here, I'm going to write plasma here. Yes. So we know this stuff. We've seen it before. Solid can go into liquid, liquid can come to become solid, right? Solid can go and become this, this can go and become this. This can become this, this can become this, this can become this, and this can become this. Yes. So that's our conversion chart I'm going to be using now. So let's just quickly bring out what each of these conversions really represents. We're familiar with some, and might not be familiar with some. So liquid going to become gas, that's easy. Don't ever write evaporation. Do not ever do that. As an A-level student, if you write evaporation, you are really wrong. Your phase diagram will make you wrong. Yes, it is vaporization. Vaporization. Because in the act of vaporization, you're going to come across two possible processes, which is what? Which is where you're going to be talking about your what? Boiling and evaporation. So we'll get there very soon. Now, in the other side, when your gas is going to become liquid, that's condensation, right? Condensation. It's just about subjecting the gas to a cool bath, or subjecting it to make contact with a cool surface, and that turns it back into liquid. Now, the way I arrange this thing is very important for you to know. I arrange this in order of increasing enthalpy. Coming there, I know why I'm doing this the way I'm doing it. Just follow me. Increasing enthalpy. Now, for your liquid to solid, that's freezing, right? That's freezing, and the reverse is melting. When you are going from solid state into liquid, that's like going from ice to liquid water. You have to melt. Gas to solid and solid to gas. We have that. Whenever it's solid turning directly into a gas, it's called sublimation. They will ask you to explain the process of sublimation using a phase diagram. It's a possible question you can see in JUPEB. Very, very possible. Explain sublimation. Explain the principles guiding sublimation, or under what condition can sublimation of carbon dioxide or water occur. You need to know those things. It's very, very simple. When we get to phase diagram, you see that. But for now, just know that sublimation is the direct conversion of solid into gas without passing through the liquid phase. Then gas to solid is called deposition, right? Deposition, yes. It's called deposition. Now we have a gas. We want to convert a gas to a plasma, right? We want to convert a gas to a plasma. That's done by ionization. So the ionization of the gas forms a plasma. So when you have an ionized gas, what you automatically form is a plasma. That's like lightning. Then when you convert plasma to a gas, that is called recombination. Chemistry question. Which of the following is the opposite interconversion process of ionization during phase change? The answer is recombination. In the biology term, we find difficult to pick that because you know recombination as another terminology. So it's recombination. Very good. Now we've arranged this in the order of increasing enthalpy. Moving from solid to liquid, you need heat. Moving from liquid to gas needs heat. Moving from gas to this needs heat. So in what we are saying now, when you heat up a solid, you form a liquid. When you heat up a liquid, you form a gas. When you heat up a gas, in essence, what am I trying to say? I'm trying to automatically tell you that following every arrow that goes like this, that goes in the direction of my something, those arrows are showing you processes that are what? Endothermic. They're showing you processes that are endothermic, processes that require absorption of heat. This process that require absorption of heat needs the absorption of heat so that their intermolecular forces can be weakened. Are you getting now? And what are those processes? It means melting. Melting is endothermic. You can see that there. So let's start tracing them out. Melting is what? Endothermic. What again is endothermic? Vaporization is endothermic. You are breaking bond. What again is endothermic? Ionization. Ionization under certain circumstances is endothermic. Chemistry, so you can see that there's a part in chemistry where they're asking you, ionization, electron affinity, which of the following is endothermic or exothermic. You can see now that ionization gas is endothermic because it's actually moving in my direction here. Okay, good. Now we have this in mind. You can define all this. I don't need to start writing the definitions for you. You know what each of these processes now mean, right? Good, sharp. Alright. Another process again that is endothermic is your what do you call it? Your sublimation. Sublimation. Very, very good. Alright, now let's come right here. A phase diagram. Now, what is a phase diagram and what's the importance of a phase diagram? A phase diagram is a diagram useful. Why? Because it's going to be showing you the different thermodynamic processes, the different physical conditions that are necessary for phase change to occur. Yes. So a phase diagram shows you the conditions. It shows you the conditions necessary. The condition necessary for what? For phase change to occur. Good. And it also enables you to see how different phases can exist at equilibrium. Yes, can exist at equilibrium. Okay. Now, let me just quickly highlight this at equilibrium here because I want to link it with this later on in phase change when we get here. Okay, now this phase diagram is usually obtained by plotting a graph of pressure for a particular substance. You are plotting a graph of pressure against temperature. So we're going to be looking at how pressure change or temperature change can affect the phase of a substance. Now, the first thing I want to ask us here is this. What are the different things you want to notice in a phase diagram before we start going to phase diagram itself? Now, parameters or components of the phase diagram you want to notice. You want to identify what the interconversion lines are. There's stuff we call interconversion lines. We'll see this very soon on the phase diagram. Those lines serve as boundaries between phases. So they serve as boundaries between phases. So anytime on the graph that you see a line, it's showing you a boundary between two phases. So that's one thing you have to take note of in that place. Another thing you have to take note of is regions, which we call phase regions. So what are these phase regions now? This is where a particular phase or state exists. So when we've said on the phase diagram, we want to take note of interconversion lines, we want to take note of regions or phase regions. Lastly, we want to take note of what? Of points. Phase points. Are you there now? Phase points. The phase points are points where equilibrium of states can exist. Yes, So very good. Now, without wasting much time, we are going to be demonstrating our phase diagram.